Good evening, everyone. My name is Hee-Won Yoon from Kyunghee University. I'm here this evening to talk to you about our team project, LMM Farm, a smart farm based on LoRa and Mqtt.
Let us first take a look at the table of contents of this presentation. The first section is the introduction. The second section, I will compare the previous works that have been done on LoRa and Mqtt. The third section, I will explain the design of LMM Farm. And the fourth section, I will explain the result of the implementation. And the last section is the conclusion.
First off, I would like to introduce my teammates. Dongjun Kim from Kyunghee University, Miran Lee from Dongguk University, and Chae Won from Seoul Women's University. We were supervised by Professor Anthony Smith from Purdue University. We are bachelor students that participated in 2019 Fall K Software Square Purdue program. In this program, computer-related majoring students from South Korea visit Purdue University to participate capstone design projects with Purdue's CIT, Computer Information Technology students. This research was supported by MSIT, Ministry of Science and ICT, Korea, under the National Program for Excellence in Software, supervised by the IITP, Institute for Information and Communications Technology Promotion. Smart farms are the future of agriculture, which are expected to increase productivity with low cost and high convenience. Nevertheless, farmers are skeptical of running smart farms due to their expensiveness, inefficient energy consumption, difficult management, and potential data leakage. Many studies suggest using LoRa, long range, a type of LPWAN, a long power wide area network technology, which is capable of long range with economical price and small battery consumption. However, there weren't any studies that focused on messaging protocols for smart farms. The size of the data received from soil moisture, temperature, humidity sensors, and weather data is very small. Hence, in order to efficiently transmit data, minimizing the wastage of packet space is necessary. In addition, the reliability and security of the data transmission must be guaranteed. There are several IoT communication protocols such as DPWS, SMPP, CoAP, but Mqtt is known to be the most suitable for IIoT, industrial IoT applications. Mqtt, Message Queue Telemetry Transport, is an extremely lightweight messaging protocol. The design principles of Mqtt is to minimize network bandwidth and device resource requirements while attempting to assure reliability and some degree of assurance of delivery. Mqtt has just 4 bytes of fixed header overhead and is the only IoT protocol that has QoS, a quality of service options, up to 3 levels. Therefore, we thought that a smart farm based on LoRa and Mqtt could meet the 5 key factors of smart farm: low cost, energy efficiency, convenient on management, data transmission, and the assurance of high security and reliability. In order for farmers to conveniently manage their smart farm, we decided to design a smart farm that can automatically control the irrigation system and provide a web-based application for monitoring and remote controlling. Here are the related works on LoRa. There was a study that demonstrated the benefits of applying LoRa technology to IoT. The study concludes that using an integration of cloud and edge computing is more appropriate than only using cloud computing in the LoRa IoT environment because it reduces the waste of resources. Another study proposed a system to control environmental factors in crop fields. They implemented a web application and mobile application, which allowed for automatic and manual control. However, they used only Wi-Fi of
the node MTU, which is different from our study, which uses LoRa network to develop a more efficient system in terms of power consumption. Also, there was a study that demonstrated through experiments that LoRa was the most efficient among many LPWAN protocols.
Here are the related works on LoRa and Mqtt. There was a study that proposed a system for building automation services using LoRa and Mqtt. This study verified that LoRa suits well in indoor scenarios, and the use of Mqtt fulfilled the real-time requirements of the building automation service. Another study proposed a marine wireless sensor network monitoring system based on LoRa and Mqtt. This study proved that even though the sensor packages in an outdoor water environment, the data from sensors don't affect significantly if the whole set of equipment is within a certain coverage of wireless signal. Lastly, there was a study that proposed a smart IoT farm model based on LoRa, and the system uploads data to the cloud using Mqtt protocol. But unlike our study on Element Farm, this system only has the monitoring part. Here are the required components for our smart farm: a Raspberry Pi, LoRa Shield, Arduino, temperature and humidity sensor, soil humidity sensor, a solenoid valve, and a high-level trigger. We used DHT11 for temperature and humidity sensor, VH400 for soil moisture sensor, a solenoid valve, and a high-level trigger for a relay module. The picture in the left is a circuit of the sensor node, and in the right is a circuit of the actuator node. The software used in this project is TTN, the Things Network Cloud, Eclipse Mosquito, an open source message broker that implements the Mqtt protocol version 5.0, 3.1N1, and 3.1. Cayenne, a IoT project builder for monitoring, and an open weather API for weather data. This is the overall system design of Element Farm. It includes 6 components as shown in the diagram: sensors, gateway, TTN cloud, irrigation node, actuator, and a web-based application. First, this is the process of how Element Farm automatically controls the irrigation system. When the sensors with Arduino and LoRa Shield collects soil moisture, temperature, humidity data, it sends the data to the gateway using LoRa RF and LoRa WAN. Then the gateway, which is a Raspberry Pi with a LoRa Shield, sends it to the TTN cloud using UDP. The TTN cloud then outlinks the data to the web server. Also, TTN Cloud sends the data to the irrigation node for edge computing using Mqtt, and the irrigation node, which is a Raspberry Pi, collects weather data using Open Weather API, and the irrigation node sends the weather data and sensor data to the gateway using Mqtt. Then the gateway decides whether to send a signal to activate or deactivate the actuator using LoRa RF and LoRa WAN. The actuators are connected to an Arduino with a LoRa Shield. Second, this is the process of how Element Farm remotely controls the irrigation system. If the farmer clicks the control button in the web-based application, the web server sends the data using Mqtt. This is an Mqtt diagram of controlling actuators automatically and when sending data to the irrigation node. In this case, the Mqtt broker is the TTN cloud and the irrigation node is the subscriber of the topic dev/test. And this is another Mqtt diagram of controlling actuators automatically when sending data to the actuators. In this case, the publisher of topic Egg IoT is the irrigation node for edge computing, and the Mqtt broker is the irrigation node, and the subscriber is the gateway. This is an Mqtt diagram of controlling actuators by farmer's decision. The web-based application is the publisher of the topic Smart Farm, and the web server is the Mqtt broker, and the gateway is the subscriber. This is a service scenario when a user operates the actuator manually using a web-based application. If the user clicks on or off button in the web-based application, the user's control is published to the broker Mqtt, and the gateway subscribes to that information. The gateway then sends a signal to the actuator using LoRa to turn the actuator on or off. The gateway responds to the changed actuator status and updates it in the database. Finally, the change result is reflected in the web-based application, and the user can see the changed result. This is a service scenario when the actuator is operated automatically without user control. The sensor node sends collected values to the gateway. The gateway uplinks to the TTN cloud, and the TTN cloud downlinks to the irrigation node, which is an edge node. Since this node has 5-day weather forecast information, it sends the weather information and the rest value to the gateway. Then the gateway uses these values and sends on or off signal to the actuator, and this process is repeated at regular intervals. This is our prototype result. The prototype was designed before installing in an outdoor farm. This prototype was implemented in a small garden inside K Software Square of Purdue University, and the web server operated on a local server. This is a demo video of the element farm activating remotely. When the user logs into the web-based application, the user can monitor all information regarding the smart farm, and when they click the actuator on button, you can see that the gateway sends a signal to the actuator. And the actuator receives the signal and turns on and opens the valve. In conclusion, in Element Farm, LoRa pays dividends on cost and power consumption, efficiency, while covering larger areas than other options. Thus, it will be practical, sensible to base LoRa as the decision on the network technology for smart farms. Also, the Mqtt protocol complements the previous smart farm studies lack on assurance on lightweight, security, and reliability of data transmission. However, this study still has its weaknesses. Managing the LoRa gateway using TTN Cloud resulted in the prerequisite of internet connection. And since the quality of internet connection at outdoors is not guaranteed, an idealistic irrigation system should be able to perform under any circumstances. Therefore, the goal of our future work is to build an entire ecosystem without the need of an internet connection. Also, to increase the feasibility of the edge logic, weather information earned from the Open Weather API will be considered. And moreover, the strengthened prototype will be implemented on an outdoor farm to verify the actual feasibility. Here are the references of the related works. Thank you for listening to our presentation on Element Farm. If you have any questions, feel free to ask.